In 2024 alone, we emitted 37.4 billion tonnes of CO2 from global fossil fuel emissions, the highest ever recorded. And for the year 2025, we are showing no sign of cutting down. These rising emissions are driving more frequent heat waves, wildfires and floods, and pushing global temperatures closer to the 1.5 degree limit set by the Paris Agreement. It's clear that cutting emissions alone won't be enough. We also need new ways to reuse the carbon we've already released. But what if we could turn our pollution into something useful? One promising approach is CO2 hydrogenation. I came across this whilst browsing the research theme Catalysis and Reaction Engineering under Dr. Wong's publications. So what exactly is CO2 hydrogenation? It's a chemical reaction between carbon dioxide and hydrogen that produces useful compounds such as methanol, methane, and other long-chain hydrocarbons. Methanol and methane are important fuels, and they are used as feedstocks to make many of the materials and products we use every day. Normally, these are sourced from natural gas, but in this process, the CO2 can be sourced from industrial exhaust or even captured directly from the air. Because CO2 is such a stable molecule, the reaction requires very high temperatures. Catalysts are needed to lower the activation energy, allowing the reaction to occur faster and under milder conditions. Much of the current research, including that of Dr. Wong's, focuses on developing catalysts that are more efficient, selective, and sustainable. CO2 hydrogenation is a key part of what some researchers call a circular carbon economy. Instead of treating CO2 as waste, we can capture it, combine it with renewable hydrogen to make fuel, and then reuse the CO2 released when that fuel burns. This could reduce our reliance on fossil fuels. While CO2 hydrogenation shows real promise, there are still important challenges to be overcome. First, the reaction requires a lot of energy, as CO2 molecules are very stable, so it often needs high temperatures and pressures, which can reduce sustainability unless powered by renewables. Another issue is hydrogen production. Most hydrogen today comes from natural gas. Green hydrogen from renewable-powered electrolysis could solve this, but it's expensive and not widely available yet. Catalysts can lose selectivity over time and produce unwanted byproducts instead of the desired fuel. Scaling up from lab experiments to industrial plants is also a complex issue. However, there are already encouraging examples, such as the MEF CO2 project in Germany, which captures CO2 from a power plant and combines it with green hydrogen to produce methanol on an industrial scale. In conclusion, CO2 hydrogenation is a promising way to use captured carbon. Combined with green hydrogen, it can enable a carbon-neutral process and lay the foundation for a circular carbon economy, where carbon is continually reused instead of wasted.